So guys, speaking of this topic, there's nothing else that I would like to add. I really do not expect anybody from you to just, watch this and to be like, okay, this is easy, I get it. So you will probably need to rewatch this, especially this second part, a few times. I would encourage you really to uh, try solving it my way, try solving it some other way, and then you would know which way suits you best. Other than that, if there are any questions, if there are any concerns, please contact me, WhatsApp or Instagram. And until next video, um, I wish you good luck and see you soon. Bye. Hello guys, welcome to my second video for the lecture 4. So just to take a look at the plan that we had in the first video, we covered differentiation rules, first and second derivative. In this video, we're going to talk about use of derivatives in analyzing functions. Okay, and I want you first to understand that I don't expect you to look at my video and to be like, okay, I understand this. This thing is, I would say, the first hard thing that we actually covered. On the internet, there are many ways to use derivatives in analyzing functions. I'm using a bit old school way, but from my experience, this one is the easiest possible one. Okay, but however, it depends on people. So if you find my way hard, which you probably will, because all ways are really hard, but so you can look the other ways up and maybe you will find something easier. I'm just talking from my experience that this one is really the easiest one. So let's go into it immediately. So I draw everything so that you guys can kind of see my point, and I hope that you can read it. So for my function, I chose the function from slide 21, function c. It's f of x equals to x to the power of 3 minus 2x to the power of 2 plus x. So the first thing that we need to find using my way in analyzing graphs will be zeros and sign. So why is this important? It will tell us when does and if our function goes through x-axis. It tells us if it's positive or negative. If it's positive, it will be above the x-axis, as you may see here, and if it's negative, it will be just under the x-axis. Okay, but let's start step by step. So first, we would take our initial function and equal it to 0 in order to find the x's. So for this one, I put the common number in front of the parentheses, so it would be x, and then inside of the parentheses I would stay with x to the power of 2 minus 2x plus 1 all equal 0. And we know that this x over here will be equals 0 when it's 0, so we can say that our x1 is 0 in the point 0, 0. In order to find two other points, we would use our quadratic formula, which we used a lot of times so far, and by applying it, we would get that x2 and x3 are both equals to 1. So we would write that 1, 0, it would be our coordinates. So what does it tell us? How to find sign based on our x's. And we know that our x's, in this case, since they're zeros, they will be also x-intercepts. It's the exact place, I should say, where our parabola or our graph will cut the x-axis. So now to find zeros, to see where it kind of starts, we would draw a little table over here where we would put our function. And for that function, I chose this one. So x from our function will go into 1, into first row here, and in another one we had what we had in our brackets, x to the power of 2 minus 2x plus 1. So now we're gonna choose 4 points. First of all, we will choose our domain, and just remember that any function has a domain that x belongs to relative numbers, which means that our domain of the function will be negative infinity and positive infinity. Okay, and these would be the two values that we're going to put first. So here we have negative infinity, and I'm going to try to zoom this in even more. So negative infinity, positive infinity. Here we would also put our points that we got for x's. Okay, and now we're going to see, by substituting these values in our functions, we're going to see what number we're going to get. In other words, is our number going to be positive or negative? Okay, so for any number between negative infinity and 0, our x will be negative. Why? So let's take a look at the number negative 2, for example. X is negative 2, meaning that x is a negative number. So we would write our minus sign here. When x is equal to 0, we would have our 0 here. So we would just circle this little line or here so that we know that that's 0. Now, for the values between 0 and 1, our x will be positive, right? Because everything that's about between 0 and 1 is positive, therefore it will be positive. The same thing will happen for values between 1 and plus infinity. So let's take a look at the number 5, for example. Is it positive? It is. So we would have our plus here. And now let's go to the second function, x to the power of 2 minus 2x plus 1. So when we take a number between negative infinity and 0, so let's take a look at the number negative 1, for example. It will be the easiest one. Okay, so substitute negative 1 instead of x. We would have 1 plus 2 plus 1, which would give us positive. So we can say that between negative infinity and 0, our function will be positive. Then we would take values between 0 and 1. So we can take 0.5 if we want. And when we substitute it in our formula, it would also give us positive number, which means that our function will still be positive. When we substitute 1, we would have 1 minus 2 plus 1, which would give us 0. So our 0 point will be here. So just circle this number so that you know that 0 is there. And then also any number that's above 1, so we can take 2. We would have 4 minus 4 plus 1, which would give us 1, which is again positive number, and it will be positive. So what does it tell us? Let's sum it up. F of x will be what? So between negative infinity and 0, our x is negative. Our actually function 1 is negative. Our function 2 is positive, which means that the overall sign will be negative. Why? Minus and plus give us minus. Right. Here we have two pluses, which would give us plus, and here we have two pluses, which would give us plus. So what does it tell us now? Now let's go back to this little terrible, spooky, creepy drawing. That tells us that our graph, our function will start in negative, will start somewhere down, but it will finish up. So it would either go like this, or like a little wave, or it will be like sine, but it will definitely not be a parabola, it will not come down. And now, when it comes to intervals, I just want to explain you what the intervals actually are, because during the lectures we mentioned the word interval. Interval is just a bit harder way to present this table. And you know, if you were following my vids from beginning, you notice that I love to work with tables because they are so organized, you just can't miss it, okay? But with intervals you can, but just to show you that this is not like science fiction or rocket science, I will just write now intervals. So what can we say? That our function f of x is smaller than 0 for which intervals? So for x belongs to this side, so you will look at this this little minus, right? So we can say it's negative for intervals between negative infinity and 0. However, it's positive for intervals 0 and 1, right? Union is just meaning end for intervals 1 to plus infinity. Never write for interval for interval between 0 and plus infinity. If there are two intervals, then just write them as two intervals. And we can say that our function f of x is equal 0 for x1 being 0 and x2 and 3 being equal 1. You don't have to write this at exam if you don't want to. Nobody will punish you. It's just so that you know what it is. It is just a bit harder way to present this information from the table. But you see, when you have this table, actually, it's not really hard to write it either. You just look at the signs here. Okay, now we have our zeros, now we have our sign. Let's take a look at the first derivative. And first derivative, we use to find the monotonicity and extremes. So what does it tell us? What is monotonicity? Monotonicity just tells us, is our graph going up or is going down? Basically, if it's increasing or decreasing. And the extremes are minimum and maximum points. So let's find the first derivative of our function. And our function was, if you remember, x to the power 3 minus 2x squared plus x. When we differentiate it, it will give us 3x to the power 2 minus 4x plus 1. Equal this to 0, so that we actually find the 2 points using our quadratic formula, because this was quadratic equation. We would get that our x1 equals 1 and that our x2 equals 1 over 3. Okay, now we're going back to drawing another table. We would, because in this case we have only one function, we would write that function here. Once again, we choose our domain points, so negative infinity, positive infinity, and we use points that we found that were our x's. And please be careful when you're writing like this. Please be careful that the smaller value comes first and then it goes bigger value and bigger and bigger and so on, depending on how many numbers you have. So it is kind of chronological. Okay? And now, as we did in our first graph, in our first table, sorry. So choose any point between negative infinity and 1 over 3. When you put it in the formula, let's say negative 1, it will give us plus. When you put this number, and we know that already, in our formula it would give us 0. And then, because that's what we got from our equation, any point between 1 over 3 and 1 would give us negative number. So you can check it also in your calculator. You know that 1 over 3 is approximately 0.334, let's say. So we can take a look at, for example, take a value of 0.5 and substitute it in the formula. It will give us the negative number. When we substitute 1 instead of x, we would get 0. Once again, it also proves the point because we got 0 in our first calculation down. And then any number that's greater than 1 would give us positive. So basically take, for example, 2 or 3, check it, and it would give us positive. So what will this tell us for our function f prime of x? It would tell us that between negative infinity and 1 over 3 it's positive, which means that it's increasing. Between 1 over 3 and 1 it's decreasing because it's negative, and between 1 and plus infinity it's increasing because, again, sign over here is positive. So that tells us two things. First thing, that this is literally what is our graph gonna look like, this little wave. But it also tells us that we would have our maximum and our minimum point. In our case, our first value, and just read it from the graph, read it from this table, sorry. Where is our max gonna be? It's increasing and then it's decreasing. So here is our maximum point. It will be 1 over 3. And then our minimum point is where it's decreasing and then increasing. So point 1 we will have our minimum point. Okay, Once again, we can write the intervals. It's just to summarize what we got in our table. I will not read this right now so that we don't waste time, but this would be also the intervals to just tell us what we found here. And now let's calculate our extremes, which means our maximum and our minimum. We said that our maximum is when x is 1 over 3. Take that value of x and substitute it in the initial equation. So instead of x to the power of 3 minus 2x to the power of 2 plus x, change x with 1 over 3. So 1 over 3 to the power of 3 minus 2 times 1 over 3 to the power of 2 plus 1 over 3. When we do that, our calculator would show us that we got 0.148. So that would be the coordinates of our max point, 1 over 3 and 0.148. For minimum, do the exactly same thing. Put the value of x into initial equation, okay, and then you will get 1 to the power 3 minus 2 to the 2 times 1 to the power of 2 plus 1. It would give us 0. So our coordinates of our minimum point are 1 and 0. When we get that, there is second last step to do, and that is to find the second derivative. It would give us convexity, concavity, and the inflection points. So what does it tell us? It will just, if it's concave, it would go like this and like this. So it just shows us when is it gonna be like little U shape, and when is it gonna be like our reverse U shape. And the inflection points. Inflection point, before I continue, it's a point where our convex curve, let's say our reverse U curve, it's going reverse U, and then when it touches inflection points, it's becoming U. So just to draw this, you know what this is. Okay, this is a map of Innsbruck, where we are right now. And you see how river goes. River is concave up. In this case, it's going up, decreasing, then it's touching this blue dot, right? And it's increasing again. Okay, so it's changed its direction. Instead of going down, it touched this blue dot and it's going up. Well, that blue dot is our inflection point. Okay, so let's take a look and try to find if we have any inflection points and where. So second derivative would be 6x minus 4. Once again, we put it equals to 0, and we find that x is equals 2 over 3. Once again, we're going to draw our table, and we would put our function 6 times x minus 4. Once again, our domains, negative and positive infinity, and our point that we calculated previously. So once again, let's check. If it's negative, it will be reverse U sign. If it's positive, it's going to be normal U sign. And now we're going to check it. So for any number that's between negative infinity and 2 over 3, our function will be negative. So let's take a look at negative 1. Negative 6 minus 4 is negative 10, which is minus. When we put our 2 over 3 into our function, we would have 0. So we just circle it here. And then any value that's greater than 2 over 3 will give us positive number. So let's take a look at, for example, number 2. 6 times 2 is 12, minus 4 is 8, which is positive number, which tell us that our second derivative of the function f of x will be negative or smaller than 0 for the intervals x belongs to all numbers between negative infinity and 2 over 3, and the shape For that range will be our reverse u, as you can see it here. It will be our function, our second derivative of the function will be greater than 0 for all x's in this range, so any x that's greater than 2 over 3, and it will be 0 at our 2 over 3. Well, now, since it's equals 0 in our, for x being 2 over 3, that means that x will be the x coordinate for our inflection point. So our inflection point is where x actually gives us 0. So now we're gonna, to find the y coordinate, we're gonna take our x value, we're gonna plug it into initial function, and then we calculate it. So it would look like, so 2 over 3 to the power of 3 minus 2 times 2 over 3 to the power of 2 plus 2 over 3. And when we put it in the calculator, it would give us a value of 0.0741, which means that our coordinates of our inflection point will be 2 over 3 for x and 0.0741 for y. Right now, knowing this, we know everything that we need to know in order to graph. So let's go back. First on our, I hope you can see this, by the way. First we're gonna find all the points that we need. So our negative infinity is somewhere down, so we can just put any random points we want, it doesn't matter. It also applies for positive infinity. It doesn't matter where you're gonna put a point here. Okay? And then our x-intercept, first x-intercept is 0, second x-intercept is 1, so we put x at 1. Our max point will have coordinates 1 over 3 and 0.148, which is here. Our minimum points has coordinates 1 and 0, which is again where our x-intercept is. And our inflection point will have coordinates 2 over 3 and 0.0741, which will be here. Knowing that, we can just connect these dots, and we know, now coming back again to our table, we know that first it starts negative, so it will go up to our maximum, it will cross our y-intercept. And actually, let me show you this. This is my drawing. It looks a bit clumsy because it is, but it is correct though. So we know that our graph is increasing to its maximum point. It's passing through y. Here, this is our maximum point. Then it's concave down. So here it's concave up. Then it's concave down. Then it's meeting our inflection point. At the inflection point, it's not concave down anymore. Now it's concave up again. So it's going down from our maximum towards our minimum. It meets our inflection point. It becomes concave up so that it's kind of curved like this. And then touches, unfortunately you can't really see it, but it touches our x-interception, so it goes to x, which is also our minimum point here, and then comes back and goes up, so it's concave up again. And when you check our tables, you will see that all information that I just said about concavity and everything is actually in our table.